It arrived from the vast emptiness of space, silent, frigid, and solitary. As it traversed the vicinity of our sun, 3IATLAS executed a maneuver that no celestial body of its kind had ever performed. It accelerated. This surge was not attributable to the pull of gravity, nor to the expulsion of gaseous jets, or the influence of the solar wind. It propelled itself. Recent findings from NASA unequivocally support this observation. A force, unseen and inexplicable, impelled it against the very fabric of gravitational attraction. Avi Loeb had foreseen this precise moment months before it transpired. He posits that it could be a remnant, a fragment of extraterrestrial engineering, a deactivated probe, or even a solar-powered sail drifting through the cosmos, gliding through our solar system. Skeptics dismiss this notion as impossible, yet the empirical data remains irrefutable. Is this the genesis of our initial encounter with another civilization? Not through dialogue, but via a subtle alteration in its velocity, a quiet greeting articulated in mathematical terms. Remain with us until the conclusion, for the revelation NASA has just unveiled might well be the inaugural tangible indication that we are not alone. If this enigma continues to hold you in suspense, much like it has me, be sure to register your approval and subscribe to ensure you do not miss a single update as this unfolds in real time. Share your thoughts in the comments, indicating your location, the current time there, and your perspective on this novel development. Part 1. Breaking News. What if we have just detected the initial technological signature originating not from Earth, but from the expanse of interstellar space? What if, at this very moment, somewhere between the planets Mars and Jupiter, a fragment of alien craftsmanship is traversing our solar system and we almost overlooked it? This is not the realm of speculative fiction. This is not a conspiracy theory whispered in the hidden recesses of the Internet. This is authentic NASA data. This is the science of orbital mechanics. This is occurring presently, and time is of the essence. On the 29th and 30th of October in the year 2025, an object designated 3IATLAS, the third officially confirmed interstellar visitor to our solar system, reached its closest proximity to the Sun. Scientists refer to this juncture as perihelion. For the vast majority of comets, perihelion is a predictable event. One calculates the gravitational influences, accounts for the solar wind, and observes the object adhering to the principles of celestial mechanics, much like a billiard ball moving across a felt surface in space-time. However, 3IATLAS deviated from this established pattern. Instead, it accelerated. Not a minor increment, not within the acceptable margins of error. It accelerated in a manner that gravitational forces alone cannot explain. NASA's Jet Propulsion Laboratory, utilizing data from the Punch satellite's Wide Field Imager 3 instrument, recorded something extraordinary. The object experienced a radial acceleration of approximately 135 kilometers per day squared, propelling it away from the Sun. Concurrently, it exhibited a transverse acceleration of about 60 kilometers per day squared, acting perpendicular to its path of travel. These figures may not hold immediate significance for you, but here is what they represent. A force acting upon this object that bears no relation to the Sun's gravitational pull or any planetary influence nudging it along. Something else is impelling 3IATLAS, something beyond our visual perception. Avi Loeb, a distinguished astrophysicist at Harvard, predicted this scenario months prior. Loeb, for those unfamiliar with his work, is the astronomer who proposed that Oumuamua, the inaugural confirmed interstellar object discovered in 2017, might not be a celestial rock, but rather a component of alien technology, perhaps a light sail or a derelict probe traversing the cosmos. The scientific establishment did not receive this suggestion favorably. They characterized it as conjecture. They labeled it as an attempt to solicit attention. Some employed even harsher descriptors. Yet Loeb remained steadfast. He advocated for an openness to extraordinary explanations when confronted with extraordinary data. And now, with 3IATLAS, the data is becoming increasingly difficult to disregard. The acceleration is not the sole anomaly. Consider its luminosity. 3IATLAS rapidly increased in brightness as it approached the Sun, a phenomenon not uncommon for comets, except that the rate of this brightening is unprecedented. Studies analyzing the object's photometry reveal a correlation between its luminosity and distance that conforms to an inverse power law with an exponent of -7.5. This is significantly steeper than the rates observed for typical comets, which generally brighten at exponents closer to -2 to -4. In layman's terms, this signifies that 3IATLAS became luminous rapidly, at a pace exceeding our predictive models for a mass of ice and rock warming under the Sun's influence. Then there is its color. Comets are expected to scatter sunlight in a manner that renders them appearing reddish or neutral in hue due to their coating of dust and organic molecules that absorb blue wavelengths. However, 3IATLAS presents an unusually blue appearance. Loeb described this as highly unexpected. The blue light suggests either extremely fine dust particles or something inherently reflective, something metallic, something that deviates from the typical characteristics of a frozen mass wandering in from the cold. Consequently, the central question, the one that is likely to occupy your thoughts for the next hour, is this: could 3IATLAS be a fragment of alien technology? Could it be a defunct probe, a portion of a light sail, or perhaps even an operational spacecraft executing a gravity assist maneuver around our Sun? And if this is the case, if this is the moment we confirm our solitude is not absolute, that intelligent civilizations have dispatched their constructs into the galaxy, what will be the subsequent events? This inquiry extends beyond a single object. It pertains to our fundamental assumptions about what visits our solar system, our understanding of the universe, and our place within it. If 3IATLAS is artificial, then every comet, every asteroid, every piece of cosmic debris becomes subject to scrutiny. We must ask ourselves, how many times have we observed something anomalous and rationalized it away because the alternative was too unsettling? How many visitors have we failed to perceive because we were not prepared to acknowledge them? Over the course of the next hour, you will be presented with the relevant data. You will hear the scientific arguments, the debates, and the institutional reactions. You will learn about the ensuing steps, which telescopes are now observing, what observations are scheduled, and what those observations might potentially reveal. But first, we must establish the robustness of this assertion. We need to delve into the measurements, the instruments, the engineers who identified the anomaly, and the scientists who are either championing or refuting it. Because here is what you must comprehend at this juncture. This matter is far from settled. The scientific community is divided. Some researchers are cautiously intrigued, others are openly skeptical, and a select few are quietly apprehensive. Their concern is not that 3IATLAS is of alien origin. Rather, it is the implication that if it is, we are utterly unprepared for what follows. We lack established protocols for such a scenario. We possess no contingency plans. We are barely equipped with telescopes aimed in the appropriate direction. Coming up next, we will explore how those numerical values were ascertained, why certain scientists are terming this the most perilous comet encounter we have never discussed, and what evidence would be required to definitively prove that we are observing something not born of nature, but crafted by intellects akin to our own, or perhaps profoundly dissimilar from some distant corner of the void. Part 2. Data and Source. Deep dive time, 0.5 seconds. The measurements that proved to be transformative originated from NASA's Punch satellite, specifically from an instrument known as the Wide Field Imager 3. Punch, an acronym for polarimeter to unify the corona and heliosphere, was designed with the primary objective of studying the Sun's outer atmosphere and the solar wind. It was not conceived as a tool for detecting extraterrestrial technology. Its purpose was to monitor the plasma and magnetic fields emanating from our star. However, it is often the case that the most significant discoveries arise when instruments are oriented correctly at opportune moments, even if their original intention was to investigate something entirely different. David Finocchia, a navigation engineer at NASA's Jet Propulsion Laboratory, meticulously analyzed the captured images. Finocchia's expertise lies in orbital mechanics, the mathematical discipline governing trajectories, and the prediction of celestial object positions based on gravitational forces and momentum. He meticulously overlaid images from the Punch instrument, tracking 3IATLAS frame by frame as it completed its passage around the Sun. What he observed deviated significantly from the theoretical predictions. The object was accelerating in ways that could not be accounted for by gravity alone. The radial component of this acceleration, directed precisely away from the Sun, registered approximately 135 kilometers per day squared. The transverse component, acting perpendicular to the line connecting the Sun and the object, was approximately 60 kilometers per day squared. To provide context for these figures, while a kilometer per day squared might seem minuscule, this acceleration compounds significantly over a period of 1 month. Loeb estimates that over a 30-day interval, this non-gravitational force would alter the object's trajectory by approximately 10 Earth radii. This equates to a deviation of roughly 80,000 kilometers. In the field of orbital mechanics, such a displacement is considered immense. It represents the difference between a comet arriving at its anticipated location and a comet appearing entirely in the wrong place, necessitating a complete reevaluation of all prior assumptions. The geometry of perihelion is crucial in this context. On the 29th and 30th of October, 2025, 3IATLAS achieved its closest approach to the Sun at an approximate distance of 1.36 astronomical units. This is equivalent to about 203 million kilometers. For comparative purposes, Earth orbits the Sun at a distance of 1 astronomical unit. Thus, 3IATLAS passed the Sun at a distance slightly greater than Earth's orbital path. This proximity was insufficient to cause vaporization, but it was close enough for solar heating to become a relevant factor. It was close enough for any volatile substances, such as water ice, carbon dioxide ice, and methane, to begin sublimating if they were present. Herein lies the characteristic behavior of comets. As they approach the Sun, they exhibit outgassing. Frozen materials on their surfaces absorb heat, transform into vapor, and are expelled outwards, producing the distinctive tails we associate with comets. This outgassing generates a reactive force, akin to a rocket engine, which subtly deflects the comet's trajectory. This phenomenon is known as the non-gravitational effect, and it is a well-documented occurrence. Astronomers incorporate this effect into their calculations when determining comet orbits. However, the non-gravitational effect is contingent upon the presence of visible gas and dust. It necessitates a coma, the diffuse cloud surrounding the nucleus. It requires spectroscopic signatures such as emission lines from water, carbon monoxide, and carbon dioxide, which confirm that the comet is actively releasing material. 3IATLAS demonstrated acceleration without any apparent outgassing. There were no discernible jets visible in the imagery, no prominent tail, and no spectral lines sufficiently strong to account for the magnitude of the observed acceleration. This is the anomaly. This is the source of contention among scientists in academic discussions and on social media platforms. Supporting the trajectory data is photometry, the measurement of brightness over time. A study titled Rapid Brightening of 3IATLAS Ahead of Perihelion, conducted by researchers including Zhang and Batams, meticulously tracked the changes in the object's luminosity as it approached the Sun. They discovered that its brightness scaled with distance to the power of -7.5. To comprehend why this is peculiar, consider that most comets brighten at rates closer to -2 to -4, depending on the volume of dust and gas they emit. A steeper exponent indicates that the object is increasing in brightness more rapidly than anticipated, either due to the production of an unusual quantity of reflective material or because its surface characteristics are undergoing unexpected modifications. Spectroscopic observations provide an additional layer of evidence. Earlier in its approach, the James Webb Space Telescope detected carbon dioxide within 3IATLAS's coma when the object was still at a considerable distance from the Sun. Carbon dioxide sublimes at lower temperatures than water ice. Therefore, its detection at an early stage is consistent with cometary behavior. However, as 3IATLAS drew nearer, the anticipated increase in water vapor, a defining characteristic of a comet nearing perihelion, did not manifest at the levels predicted. While some water was detected, it was insufficient to explain the observed acceleration or the rapid increase in brightness. NASA's own factual documentation corroborates the established timeline. The object reached its closest proximity to the Sun on the 29th and 30th of October at approximately 1.4 astronomical units, aligning with the perihelion window reported by JPL. The photometry, the trajectory data, and the spectroscopy collectively point to a singular conclusion. Something anomalous is occurring, something that does not readily fit within our established models of cometary behavior. However, models are precisely that, models. They are approximations built upon underlying assumptions. They presume specific compositions, particular surface properties, and predictable thermal responses. When an object behaves in a manner that deviates from these expectations, it does not automatically imply that the object is artificial. It may simply signify that our assumptions are flawed. This is the argument advanced by the skeptics, and it is a compelling one. Scientific progress is achieved through the refinement of models, not by precipitously leaping to extraordinary conclusions. Nevertheless, the uncertainties inherent in the data are substantial. Astrometric fits, the mathematical process of aligning observed positions with predicted trajectories, inherently include error margins. Varied assumptions regarding the object's mass, its surface reflectivity, and its rotational rate all influence these calculations. Photometry is dependent on the methodology employed for modeling the dust-to-gas ratio, the distribution of particle sizes, and the surface albedo. Minor adjustments in these assumptions can lead to significant alterations in interpretation. To illustrate this point, consider an analogy. Imagine observing a car traveling along a highway. You are aware of the speed limit and the engine's capacity. Based on the principles of physics, you can calculate the expected speed of the car and its precise location at any given moment. Now, picture the car beginning to accelerate without the driver engaging the accelerator pedal. There is no apparent cause, no audible increase in engine revs. The car simply speeds up. You consult your instruments. You re-examine your assumptions. Perhaps there is an auxiliary motor. Perhaps the road is inclined. Perhaps there is a strong wind. However, if you systematically eliminate all plausible natural explanations and the car continues to accelerate, you would inevitably begin to question whether some unaccounted-for factor is at play. This is precisely the situation we find ourselves in with 3IATLAS. The upcoming observations scheduled for early November and mid-December of 2025 will either definitively resolve this enigma or dramatically escalate its intrigue. Part 3. Loeb's Interpretation versus Natural Hypothesis. Two fundamentally opposing frameworks currently dominate the discourse. On one side, the natural explanation posits that outgassing and sublimation generate thrust, and that the emission of dust and gas accounts for increases in luminosity, with 3IATLAS representing an extreme manifestation of cometary behavior. On the other side, the speculative hypothesis proposes an artificial origin, such as radiation pressure acting upon a light sail, an internal propulsion system, or an engineered construct designed for interstellar navigation. Both frameworks find partial validation within the data. Neither, however, accounts for all observations with complete accuracy. Avi Loeb's line of reasoning commences with an examination of mass loss. If the observed acceleration is indeed a consequence of outgassing, if sublimating ice is producing the propulsive effect that is deflecting the object, then it is possible to calculate the quantity of mass the comet must be expending. The figures derived from this calculation are remarkable. To achieve an acceleration of 135 kilometers per day squared, a comet would be required to vent a substantial proportion of its total mass over a period of weeks or months. Loeb contends that such extensive mass loss should be readily detectable. It should manifest as a visible gas plume, a prominent tail, and discernible spectral signatures that instruments like the Hubble Space Telescope or the James Webb Space Telescope could easily identify. However, these expected signatures have not materialized, at least not to the extent anticipated. While some carbon dioxide was detected at an earlier stage and some water vapor has been observed, the emission levels are too faint to account for the magnitude of the acceleration. This scenario is analogous to observing a rocket launch without witnessing the exhaust plume. The effect is evident, but the cause remains elusive. Loeb also draws attention to the anomaly in the object's color. Comets scatter sunlight, and the dust they expel typically absorbs blue wavelengths, resulting in reflected light appearing reddish or neutral. Conversely, 3IATLAS exhibits a distinctly blue hue. Loeb describes this as highly unusual, noting that blue light is indicative of either exceedingly fine dust particles, far finer than those typically associated with comets, or a reflective surface possessing properties more consistent with metallic or engineered materials. While natural processes can produce fine dust, it is not a common occurrence, nor is it typically produced in quantities sufficient to explain both the observed brightness and color. Therefore, what might an artificial origin entail? One plausible explanation involves a light sail. Light sails are exceptionally thin, reflective structures designed to be propelled by radiation pressure, which is the momentum imparted by photons emanating from a star. Scientists have proposed light sails as a method for propelling spacecraft across vast interstellar distances without the need for conventional fuel. A sail of sufficient size and minimal mass could, in theory, be accelerated by sunlight. As the sail approaches a star, the radiation pressure intensifies, propelling the sail at an increased velocity. Near perihelion, this effect would be most pronounced, generating precisely the type of radial acceleration observed in 3IATLAS. The mathematical calculations involved are complex but not insurmountable. While radiation pressure at 1.36 astronomical units is less intense than at Earth's orbital distance, it is still measurable. For a sail possessing the appropriate area-to-mass ratio, one that is exceptionally thin and highly reflective, it is feasible to generate accelerations within the approximate range of what has been observed. The primary challenge lies in the fact that such a sail would need to be extraordinarily thin, perhaps only micrometers thick, and possess a reflectivity approaching 1, indicating near-perfect reflection. This level of precision is achievable with engineered materials, but is highly atypical for natural celestial objects. Another potential explanation involves an internal propulsion system. Envision a spacecraft executing a burn maneuver in close proximity to perihelion, utilizing the Sun's gravitational influence to amplify its velocity change. This is a standard maneuver in orbital mechanics known as a powered gravity assist. Human spacecraft routinely employ this technique. Engines are fired at the point of closest approach to maximize the efficiency of the propulsive burn. If 3IATLAS were such a spacecraft, it might be performing a maneuver specifically designed to alter its trajectory for reasons yet unknown to us. Loeb acknowledges that this is speculative, and his assessment is accurate. There is no direct evidence of an engine, no detectable thermal excess, and no observable exhaust signature. However, the absence of evidence is not evidence of absence, particularly when the instruments employed were not designed to detect such specific signatures in the first place. Loeb has also suggested that 3IATLAS represents the 9th anomaly associated with the object's behavior, implying that it already possesses a documented list of unusual characteristics. He has been diligently monitoring this object, drawing comparisons to Oumuamua, the first interstellar visitor, which also exhibited non-gravitational acceleration without apparent outgassing. The parallels are compelling. Both objects are of interstellar origin. Both displayed anomalous motion. Both lack the clear cometary characteristics one would typically expect. A single data point may be considered an outlier. However, 2 data points begin to suggest a pattern, and patterns, by their nature, necessitate an explanation. Yet, patterns can also be misleading. Confirmation bias poses a genuine risk in scientific inquiry. When one is actively seeking evidence of alien technology, it becomes facile to perceive it everywhere, even within data sets that possess more conventional explanations. Critics of Loeb's approach frequently highlight this concern. They argue that he selectively chooses anomalies, disregards data that contradicts his hypothesis, and overstates the improbability of naturalistic explanations. Therefore, the subsequent course of events hinges upon the observations slated for November and December of 2025. If these observations detect significant outgassing, if they reveal water vapor and carbon monoxide in quantities sufficient to account for the observed acceleration, then the naturalistic explanation will prevail. 3IATLAS will be deemed merely an unusual comet, an extreme case, but ultimately a natural phenomenon. The case will be closed, and Loeb's speculations will recede into the background. However, if these forthcoming observations fail to detect adequate outgassing, if the acceleration persists without an identifiable source, then the hypothesis of artificial origin becomes considerably more difficult to dismiss. It will transition from the realm of fringe speculation to a serious possibility. And at that juncture, the nature of the conversation will fundamentally change. We will no longer be discussing comets and orbital mechanics. We will be addressing contact, technology, intelligence, and the profound implications for humanity's position within the cosmic order. Part 4, Controversy, Institutional Response, and Public Reaction. The scientific community is far from a unified entity. This gathering comprises individuals possessing distinct educational backgrounds, inherent predispositions, and varying degrees of comfort with risk and speculation. When Avi posits the notion that an artifact might represent extraterrestrial engineering, certain investigators perceive a provocative thinker challenging established paradigms. Others, however, view a researcher sacrificing scientific rigor for fleeting public attention. Both perspectives possess validity and collectively influence the unfolding narrative surrounding the 3IATLAS imbroglio. The scientific establishment focused on cometary studies has largely adopted a cautious stance. Many contend that while the gathered data is indeed irregular, it does not yet provide sufficient justification for making extraordinary pronouncements. Comets are inherently intricate entities. Their exterior surfaces are characterized by a lack of uniformity. Pockets of volatile constituents can sublimate unevenly, generating propulsive forces that deviate from a direct outward vector away from the Sun. These forces can induce rotational stresses that alter the object's spin rate, which in turn impacts how the comet reflects solar illumination and its acceleration. The process of simulating these phenomena necessitates detailed hypothetical constructs, and these constructs are invariably accompanied by inherent uncertainties. The prevailing argument suggests that until all plausible terrestrial explanations have been thoroughly investigated and dismissed, we should refrain from invoking the hypothesis of alien technological origins. This position is entirely defensible. Scientific inquiry is fundamentally conservative in its design principles. Assertions that are extraordinary demand correspondingly extraordinary substantiation. As it stands, the evidence supporting the artificial nature of 3IATLAS is not yet extraordinary. Rather, it is suggestive and intriguing. However, suggestion and intrigue do not equate to definitive proof. Furthermore, there exists another facet to this dispute that is entirely unrelated to the scientific data itself. It pertains to the conduct of institutions, the principles of openness, and the establishment of confidence. Loeb has publicly leveled accusations against NASA, alleging that the agency has either deliberately delayed or withheld certain observational findings. Specifically, he has asserted that an image captured by the high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter on October 2, 2025, has not been disseminated. The high-rise instrument is equipped to procure images of exceptional detail, and had it been directed at 3IATLAS during the object's approach, such an image could contain pivotal information regarding the object's surface composition, its geometrical configuration, its light-reflecting properties, and whether it exhibits any characteristics incompatible with a natural cometary body. NASA has thus far not issued a public response addressing this particular allegation. This reticence has served to intensify conjecture. Across social media platforms, unsubstantiated theories have flourished. Certain users propose that NASA is intentionally suppressing evidence on the grounds that the object is indeed of artificial manufacture, and that the agency wishes to avoid inciting widespread public apprehension. Conversely, others maintain that the delay is attributable to bureaucratic processes, that the release of images undergoes standard review protocols, and that there is nothing untoward in this procedure. The reality likely occupies a middle ground. Space exploration agencies tend to be circumspect regarding the dissemination of data that might be subject to misinterpretation. They also exercise caution in releasing information prior to its thorough calibration and validation. However, this cautious approach can be perceived as obfuscation, particularly when prominent scientific figures publicly advocate for greater transparency. Adding further fuel to this contentious situation is NASA's public communications strategy. In late October, the acting administrator of NASA responded to an inquiry posed by a notable Internet personality, reportedly Kim Kardashian, although the precise details vary according to the source, concerning whether 3IATLAS presented a potential hazard or was of extraterrestrial origin. The administrator's reply was direct and unequivocal. No aliens, no threat. While this statement was intended to allay public concerns, it had the contrary effect on certain segments of the audience. To critics, it sounded dismissive, as if NASA were downplaying legitimate scientific inquiries in an effort to circumvent controversy. This inherent tension between transparency and prudence is not a novel phenomenon. Space agencies have consistently navigated a delicate equilibrium when confronted with anomalies that might suggest extraordinary explanations. They aim to avoid propagating unfounded speculation, while simultaneously striving to appear as though they are not withholding information. The challenge lies in the contemporary digital landscape, where every decision is subjected to intense scrutiny, every delay is met with questioning, and every utterance is meticulously dissected for underlying implications. The International Asteroid Warning Network, a collaborative body comprising space agencies and astronomical observatories, initiated a specialized campaign focused on comets in response to the emergence of 3IATLAS. This campaign, scheduled to run from November 2025 through January 2026, is designed to synchronize observations from a multitude of telescopes and instruments, pooling their collected data to establish the most precise possible depiction of the object's nature and its observed behavior. On the surface, this undertaking appears to be a standard scientific procedure. An unusual celestial object warrants a coordinated response and rigorous analysis. However, some interpret the activation of this campaign as definitive evidence that the agencies are treating the anomaly with considerable seriousness, perhaps even more so than they are willing to publicly acknowledge. The question arises, why institute a synchronized campaign for a comet unless there is perceived value in its investigation? Why engage such a vast array of telescopes unless the stakes exceed those of routine observation? Public perception has undergone a rapid transformation. Prior to October, 3IATLAS was a minor curiosity within the astronomical community, one among several interstellar entities detected in recent years. It has now become a cultural touchstone, trending on social media and becoming a focal point for discussions on podcasts, in YouTube videos, and across news outlets. People are actively posing fundamental questions. Are we solitary in the universe? Is this the pivotal moment that alters our understanding of existence? Can we place our trust in NASA? This last inquiry carries the greatest potential for disruption. Confidence in established institutions is inherently fragile. When individuals perceive that information is being managed or withheld, they tend to fill these perceived voids with speculation, which can then escalate into profound distrust. Scientists like Loeb, who are prepared to publicly challenge established institutional narratives, often become central figures in these debates. They are lauded by some as champions of truth and criticized by others as seeking personal notoriety. The reality, as is often the case, is far more complex. What would transpire if the evidence were to strongly indicate an artificial origin? This is a scenario that few are willing to address openly, yet it occupies the thoughts of many in private. Should 3IATLAS ultimately prove to be a product of extraterrestrial engineering, the ramifications would be staggering. Policymakers would undoubtedly become involved. Oversight mechanisms akin to those used in SETI, Search for Extraterrestrial Intelligence, research might be implemented. Governments would be compelled to seek answers to critical questions. Is it a probe? Is it operational? Does it pose a threat? Or does it represent an opportunity? And if such a scenario were to unfold, the current discourse concerning comets and orbital mechanics would likely seem quaintly simplistic in hindsight. Part 5. Immediate Stakes and Upcoming Observations. The temporal framework for the ensuing months is of paramount importance. All subsequent developments hinge upon observations scheduled for November and December of 2025. These are not routine follow-up procedures, rather, they represent targeted campaigns involving some of the most sophisticated telescopes and instruments ever conceived by humanity. The findings derived from these observations will either definitively resolve the 3I-ATLAS situation or elevate its mystery to an unprecedented and potentially overwhelming level. The European Space Agency's JUICE mission is positioned to be among the first to contribute to this effort. JUICE, an acronym for Jupiter Icy Moons Explorer, is presently en route to Jupiter with the objective of studying Europa, Ganymede, and Callisto. However, the nature of orbital trajectories can be unpredictable. Occasionally, spacecraft inadvertently pass in close proximity to objects of significant interest. In early November of 2025, JUICE is projected to traverse a path relatively near to 3I-ATLAS. According to orbital calculations, the closest approach distance during this flyby is estimated to be approximately 0.428 astronomical units, which translates to roughly 64 million kilometers. While this distance is substantial by terrestrial standards, within the vastness of space, it constitutes a near pass. JUICE is equipped with both cameras and spectrometers. Should the geometrical alignment of the flyby prove favorable, it could yield images of 3I-ATLAS with a higher resolution than any previously obtained. Furthermore, it possesses the capability to analyze the spectrum of reflected sunlight, searching for indicators of specific molecular compositions or materials. Should 3I-ATLAS exhibit signs of outgassing, JUICE might detect such emissions. If the object displays unusual surface characteristics, such as facets, intricate structures, or reflective patches, JUICE might be able to discern them. Avi Loeb has been particularly vocal regarding the significance of the JUICE observations. He has posited that if 3I-ATLAS is indeed a naturally occurring comet, then JUICE should detect unambiguous evidence of gas emission, including water vapor, carbon monoxide, and potentially ammonia or methanol. If these signatures are present in quantities sufficient to account for the observed acceleration, then the natural explanation would be vindicated. Conversely, if these signatures are absent or demonstrably weak, the hypothesis of an artificial origin would gain considerable credence. Later in December, around the 19th, both the Hubble Space Telescope and the James Webb Space Telescope are slated to conduct observations of 3I-ATLAS. Hubble's expertise lies in the visible and ultraviolet wavelengths, making it ideally suited for detecting spectral lines indicative of gas emission and quantifying the manner in which light scatters from the object's surface. JWST, operating in the infrared spectrum, is exceptionally adept at detecting thermal radiation and identifying heat signatures that could suggest internal activity or anomalous surface properties. These forthcoming observations will possess a sensitivity level unparalleled by any previous data acquisition. If 3I-ATLAS possesses any surrounding gaseous envelope, Hubble and JWST are likely to detect it. If dust particles are present, their composition and size distribution will be meticulously measured. Should thermal anomalies, such as hotspots, cold regions, or asymmetrical temperature distributions, be present, they will be comprehensively mapped. The resultant data will be subjected to analysis by multiple independent research teams, thereby ensuring that no single interpretation gains undue prominence without thorough peer review. Ground-based observatories are also integral to this coordinated effort. Telescopes situated in Chile, Hawaii, and the Canary Islands are all participating in the collective campaign. Spectroscopic observations will meticulously track variations in the object's emitted light over time, searching for periodic fluctuations that might correlate with rotational movements or the intermittent visibility of surface features. Photometric monitoring will quantify changes in brightness, thereby refining models that describe how the object interacts with and reflects solar illumination. The potential outcomes of these investigations can be broadly categorized into two distinct scenarios. Scenario A posits that the observations will reveal sufficient outgassing and dust production to adequately account for both the observed acceleration and the anomalous brightness. In this eventuality, 3I-ATLAS will be definitively classified as a natural comet, albeit one exhibiting unusual characteristics. Scientific publications will emerge detailing its composition, its active processes, and the factors distinguishing it from other comets. The event will then recede into the historical record of interstellar objects recognized as interesting and instructive, but ultimately not transformative. Scenario B posits that the observations will fail to detect adequate levels of gas or dust to explain the object's acceleration. The object will continue to accelerate without any discernible source of propulsion. Spectroscopic analysis will reveal surface properties that are incongruent with those typically observed in comets. Thermal imaging will identify anomalies. Under this scenario, the hypothesis of an artificial origin would transition from the realm of speculation to that of plausible consideration. Scientists would begin to pose more profound and probing questions. Mission proposals would be drafted with increased urgency. CT researchers would become actively involved. Policymakers would receive briefings. Should Scenario B materialize, subsequent actions could encompass the deployment of targeted missions. Proposals for spacecraft designed to intercept 3I-ATLAS while it remains within accessible proximity might be fast-tracked. A flyby mission would afford the opportunity to acquire close-range imagery, ascertain the object's mass and density, and conduct an exhaustive analysis of its surface. A rendezvous mission would involve orbiting the object, facilitating its study over an extended period of weeks or months. If the object is indeed artificial, such undertakings would represent some of the most significant scientific endeavors in human history. Furthermore, the impact on public perception warrants consideration. If the evidence increasingly points towards an artificial origin, the credibility of established institutions will be rigorously tested. The public will demand answers, seeking to understand what governments knew when they acquired such knowledge, and the rationale behind the dissemination or withholding of that information. The media would undoubtedly amplify the narrative, and social media platforms would erupt with a torrent of theories, debates, and fervent calls for openness. This juncture represents a critical turning point for contemporary astronomy. For decades, humanity has diligently searched for indicators of intelligent life beyond Earth. Radio telescopes have been directed towards distant stars in anticipation of receiving signals. The atmospheres of exoplanets have been meticulously analyzed for biosignatures. Frameworks have been developed for the detection of technosignatures, such as megastructures, Dyson spheres, or laser pulses, any of which might signal the presence of advanced civilizations. However, there has always been an underlying assumption that any such discovery would be situated at an immense distance, light years away, rendering it abstract and safely removed. 3I-ATLAS, by contrast, is not distant. It is here, within our solar system. It is sufficiently close for detailed study, within reach for potential interception, and proximate enough to compel us to confront the profound possibility that we are not solitary, and that the evidence has been drifting past us all along, awaiting a sufficiently discerning gaze. The forthcoming months will determine whether this is indeed the case. We will either conclude our investigation of 3I-ATLAS and revert to conventional scientific pursuits, or we will inaugurate a new epoch in human history, one in which the cosmos is no longer perceived as empty, but rather as replete with diverse intelligences and sophisticated machinery, prompting questions that we are only now beginning to formulate. We have now examined the assertion, the supporting data, and the inherent stakes involved. In the subsequent segment, we will delve deeper into hidden trajectories, enigmatic brightness fluctuations, conspiracy theories, fundamental physics, and speculative scenarios that challenge the very limits of our comprehension. Part 6. Trajectory and Kinematic Context. To comprehend the provenance of 3IATLAS, one must first grasp the nature of interstellar space. The galaxy is not a void. It is populated by clouds of gas and dust, rogue planetary bodies, comets ejected from their original systems, and debris resulting from stellar collisions. These entities traverse the interstellar medium for epochs spanning millions or even billions of years, their movements dictated by the subtle gravitational forces exerted by distant stars. Their trajectories are shaped by the gradual, ponderous progression of galactic dynamics. The vast majority of these objects will never approach another star system. They will perpetually wander in the darkness. However, on occasion, one such object will draw sufficiently near to a star like our Sun to be temporarily ensnared by its gravitational pull, traversing the solar system along a hyperbolic path before re-emerging into the cosmic void. 3IATLAS represents the third such confirmed interstellar object. The first was Oumuamua, identified in 2017. The second was Comet Borisov, discovered in 2019. Both were unequivocally recognized as interstellar due to their hyperbolic orbits, indicating velocities exceeding the solar system's escape velocity. They were not gravitationally bound to the Sun. They were mere transient visitors. Population models suggest that interstellar objects of this nature are commonplace. A research paper by Hopkins and Dorsey, titled "From a Different Star," estimated that at any given moment there are likely thousands of interstellar objects within the orbital path of Neptune. The majority are too diminutive or too faint to be detected by current astronomical instruments. This implies that we are not observing rare occurrences, but rather the most conspicuous portion of a phenomenon that is continuously unfolding around us, largely unnoticed. 3IATLAS possesses a velocity at infinity, which is its speed in the absence of the Sun's gravitational influence, estimated to be between 20 and 30 kilometers per second, contingent upon the precise orbital solution. This velocity is considerable by solar system standards, but is typical for interstellar objects. Its orbital inclination, which denotes the angle of its path relative to the plane of the solar system, is substantial, ranging from approximately 70 to 80 degrees. This is another characteristic hallmark of interstellar origin. Objects within our solar system tend to orbit along a similar plane, having coalesced from the same primordial protoplanetary disk. Interstellar objects, by contrast, arrive from random directions, their inclinations reflecting the chaotic dynamics of the galaxy. Ascertaining their precise point of origin is considerably more challenging. It is possible to trace an object's trajectory backward in time, accounting for the Sun's gravitational influence and the gravitational effects of the planets. However, once the path extends into interstellar space, the inherent uncertainties escalate. Minor inaccuracies in the measured velocity or position compound significantly over extended periods. Despite these challenges, researchers have undertaken such analyses. Certain models propose that 3IATLAS originated within the thin disk of the Milky Way, the region that hosts the majority of stars and planetary systems. Other models suggest an origin in the thick disk, an older and more dispersed stellar population exhibiting different kinematic properties. The thick disk hypothesis is particularly compelling as it suggests the object could be billions of years old, a relic from an earlier phase of galactic evolution. Could it have encountered other star systems? Almost certainly. Over billions of years, an object drifting through the galaxy would inevitably pass through numerous stellar neighborhoods, traversing within a few light years of dozens or even hundreds of stars. Each such encounter would subtly alter its trajectory. Over vast timescales, the original orbital path would be erased, supplanted by a trajectory shaped by countless gravitational perturbations. If 3I-ATLAS is indeed artificial, its history then raises pertinent questions. Was its trajectory deliberately plotted? Did it originate from a star system that we can currently identify? Or has it been adrift for such an extended period that its original source is now lost to time? The issue of human-made spacecraft also arises. Humanity has dispatched several probes into interstellar space or onto trajectories that will eventually lead them beyond the confines of the solar system, including Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons. All of these craft are traveling at speeds slower than 3I-ATLAS. If 3I-ATLAS is artificial, its velocity surpasses that of any spacecraft we have constructed, implying either a more advanced propulsion system or a prolonged period of acceleration, perhaps involving a light sail propelled by starlight over centuries or millennia. The JUICE flyby in early November adds another intriguing dimension to this enigma. JUICE is currently navigating through space en route to Jupiter, and its trajectory serendipitously brings it into relatively close proximity with 3I-ATLAS. Relatively, of course, is a subjective term. A distance of 0.428 astronomical units, approximately 64 million kilometers, is far too great for detailed imaging by JUICE's cameras. However, it may be sufficiently close for spectroscopic analysis, provided the geometrical alignment and timing are opportune. JUICE was not originally designed for the study of interstellar objects, but serendipitous opportunities sometimes arise, and this appears to be one such instance. Furthermore, the passage of 3I-ATLAS through regions of interesting plasma or magnetic fields could also be significant. The solar wind, a continuous stream of charged particles emanating from the Sun, interacts with any object that intercepts its path. If the object possesses a magnetic field or a charged surface, this interaction can generate detectable signatures. If 3I-ATLAS is artificial, perhaps a spacecraft constructed with conductive materials, the solar wind might produce a wake or disturbance that deviates from what would be expected for a natural comet. The proximity of its trajectory to other spacecraft also warrants consideration. For instance, Mars orbiters have previously captured images of comets. The Mars Reconnaissance Orbiter, equipped with its high-resolution camera, is capable of achieving extraordinary levels of detail. If it were directed towards 3I-ATLAS during the object's approach, it could have acquired imagery revealing features imperceptible to ground-based telescopes. Whether such an image exists and has been publicly released remains a central point of contention in the ongoing controversy. The orbital path of 3I-ATLAS is also a crucial factor for future observational efforts. As the object recedes from the Sun, its observable brightness will diminish. The intensity of reflected sunlight decreases with distance, and eventually, even the most powerful telescopes will struggle to detect it. Consequently, the window for observation is rapidly closing. If essential information is not acquired within the next few months, the object will drift beyond our observational reach, vanishing into the darkness. However, here lies a speculative but compelling possibility. If 3I-ATLAS is artificial and was dispatched from a planetary system within the thick disk billions of years ago, its passage through our solar system might not be a random occurrence. It could be one instance within a larger pattern. We might be observing a single data point in a more extensive distribution, a pattern that will only become apparent once a sufficient number of interstellar objects have been identified, allowing us to discern statistical fingerprints of intentional voyages rather than mere random drift. This thought leads to a question that warrants profound contemplation. How many such objects have eluded our detection? How many have traversed the inner solar system before we possessed the technological capacity to observe them? How many are presently out there, too faint or too distant to be detected, potentially carrying information, advanced technology, or simply drifting as silent monuments to long-extinct civilizations? The trajectory of 3IATLAS is more than just a line traced through space. It is a potential link connecting us to the profound possibility that the galaxy is not silent or empty, but teeming with travelers akin to this one, and that we are only now commencing the arduous task of learning how to perceive them. Part 7. Brightness Law. Anomalies and Photometry Detail. Numerical data possesses the capacity to convey narratives, provided one possesses the skill to interpret it. The observed brightness of 3IATLAS adheres to a power law relationship. Specifically, its brightness is inversely proportional to the distance raised to the power of -7.5. Mathematically speaking, the object's brightness corresponds to a constant multiplied by the inverse of its distance raised to the 7th.5 power. For those unfamiliar with mathematical expressions, this indicates that as the celestial body draws nearer to the sun, its luminosity increases at a far more rapid pace than one would typically anticipate for a common comet. While most comets do indeed become more luminous as they approach the sun, this intensification is generally more gradual, usually adhering to an exponent between -2 and -4. An exponent of -2 signifies that the brightness escalates with the square of the diminishing distance. Conversely, an exponent of -7.5 implies that the brightness rises with nearly the 8th power of the decreasing distance. This is not a minor disparity. It represents a profound difference, the kind that compels astronomers to pause and question the underlying phenomena. Several physical mechanisms could account for such an exceptionally steep increase in brightness. One hypothesis involves exceedingly fine dust particles. When sunlight scatters off particles, the effectiveness of this scattering is contingent upon their size. Smaller particles interact with light differently than larger ones. If 3IATLAS is generating exceptionally fine dust, with particles measured in micrometers rather than millimeters, this could amplify its brightness more swiftly than standard predictive models suggest. However, the generation of such fine dust necessitates processes like fragmentation, collisions, or sublimation, all of which break down larger grains into smaller ones. Typically, these processes occur when a comet is highly active, expelling substantial volumes of gas and dust. Yet, 3IATLAS does not exhibit the gaseous signatures one would expect from such elevated activity. Another possibility is the rapid sublimation of volatile substances. Carbon dioxide ice undergoes sublimation at lower temperatures compared to water ice. Consequently, as a comet approaches the sun, carbon dioxide can begin to vent before water does. If 3IATLAS is exceptionally rich in carbon dioxide, or if it harbors other volatiles, such as carbon monoxide or methane, these substances could be driving the observed brightness enhancement. Initial observations conducted with the James Webb Space Telescope did detect carbon dioxide within the coma when the object was situated at a greater distance from the sun, lending support to this theory. Nevertheless, the quantity of gas detected still appears insufficient to fully explain both the luminosity curve and the object's acceleration. Furthermore, there is the phenomenon of thermal fracturing. As a comet heats up, thermal stress can cause its surface to crack, thereby exposing fresh ice beneath. This newly revealed ice is more reflective than weathered ice, so the uncovering of fresh material could trigger a sudden surge in brightness. This mechanism has been observed in other comets, particularly those with layered or heterogeneous surfaces. However, thermal fracturing typically results in transient brightness spikes. The object briefly intensifies in luminosity before stabilizing or dimming as the exposed ice sublimes away. The brightness trajectory of 3I-ATLAS seems more consistent with an ongoing process rather than a singular event. And then there is the speculative alternative: internal heating or engineered reflectivity. If 3I-ATLAS possesses an internal energy source, perhaps a decaying power source, or an active engine generating heat from within, this could warm its surface in ways not attributable solely to solar radiation. Alternatively, if the object features a reflective surface with unusual properties, potentially designed to maximize or minimize light reflection at specific wavelengths, this could produce a luminosity profile that deviates from natural models. A comparison with other interstellar objects offers valuable insights. The first known interstellar visitor, Oumuamua, displayed no visible coma or tail, nor any apparent signs of outgassing. Despite this, it exhibited non-gravitational acceleration, leading some researchers, including Avi Loeb, to propose it might be a light sail or a fragment thereof. Comet Borisov, the second interstellar object detected, behaved much more like a conventional comet. It possessed a discernible coma, a tail, and spectroscopic signatures consistent with water and carbon monoxide. While it brightened as it neared the Sun, its luminosity curve followed more conventional exponents. 3I-ATLAS occupies an intermediate position between these two extremes. It demonstrates some level of gas emission and activity, yet not enough to account for its observed acceleration or its rapid brightening. It presents as anomalous, without being entirely inexplicable by natural means, at least for now. Color indices introduce another layer to this enigma. Photometry not only measures overall brightness, but also quantifies it across different wavelengths. By comparing an object's luminosity in blue light versus red light, astronomers can infer characteristics of its surface or dust composition. Typical comets exhibit slightly reddish color indices, a consequence of their dust preferentially scattering longer wavelengths. However, 3I-ATLAS appears distinctly blue. A blue color suggests either the presence of extremely small particles that efficiently scatter blue light, or a highly reflective surface with a substantial albedo in the blue portion of the spectrum. Observations from instruments like the Subaru telescope's Suprime Cam and the triple-spec spectrograph have indeed measured color magnitude differences, confirming this unusual blue hue. While not entirely impossible for a natural comet, it is certainly atypical. When the blue coloration is considered alongside the steep luminosity curve and the paucity of strong gas emissions, it becomes clearer why certain scientists are intrigued while others remain skeptical. Each of these anomalies, considered in isolation, might have a natural explanation. However, taken together, they form a pattern that is more challenging to disregard. Recent preprints on the Archive repository for scientific research have included measurements of water production rates at distances exceeding 3 astronomical units. Water ice sublimes at temperatures corresponding to proximity to the Sun. Therefore, detecting water at such early stages suggests either highly efficient heating or the presence of exposed pockets of volatile, rich material on the surface. Nevertheless, the reported water production rates, while noteworthy, are not substantial enough to account for the acceleration observed near perihelion. This discrepancy between expected and observed behavior lies at the core of the mystery. This juncture invites compelling speculation. What if the observed brightness surge is not attributable to dust or gas, but rather to the exposure of metallic surfaces? If 3I-ATLAS were a fragment of artificial technology, a damaged sail, a non-functional probe, or debris from an ancient collision, it might possess reflective materials that behave differently from ice or rock. Metals, particularly polished or engineered surfaces, possess high albedos and reflect light in ways that are dependent on the angle of incidence and the wavelength of light. A tumbling object with metallic facets could generate brightness fluctuations that do not align with cometary models. Alternatively, consider the possibility of internal luminescence. This represents the most extreme speculation, but if 3IATLAS harbors an internal energy source, perhaps still partially operational after eons of travel, this energy could manifest as heat or light. A spacecraft with a degrading power system might emit infrared radiation detectable by instruments like the JWST. A probe with malfunctioning systems could exhibit localized hotspots where electronics are still drawing power. These are not hypotheses one readily introduces in a peer-reviewed publication, but they are certainly contemplated during late-night contemplation when data stubbornly resists integration into established models. The anomalies in brightness are not definitive proof of any particular scenario. Rather, they serve as clues, like breadcrumbs, leading deeper into an unknown territory, prompting questions about whether one is following a path to discovery or becoming lost in a labyrinth of coincidences. Part 8 delves into conspiracies, data transparency, and inherent biases. What if the reason for our surprise regarding 3IATLAS stems not from the object itself being inherently surprising, but from our not having access to all the relevant data? It is conceivable that images, spectra, and measurements exist on servers somewhere, having undergone review by a select group of scientists, but have not been released to the public for reasons ranging from administrative hurdles to more sinister motives, depending on one's perspective. Avi Loeb has publicly stated that NASA has withheld imagery from the Mars Reconnaissance Orbiter. Specifically, he claims that the HiRISE camera, a high-resolution instrument aboard the orbiter, captured an image of 3IATLAS on October 2, 2025, which has yet to be released. HiRISE is among the most powerful cameras in orbit, capable of resolving features as small as 1 meter across on the Martian surface. If directed at an interstellar object, it could potentially reveal details imperceptible to ground-based telescopes, such as surface texture, shape, and possibly even structures or features that would definitively resolve the question of its natural or artificial origin. Several explanations for the withholding of such an image are possible, spanning a spectrum from the mundane to the conspiratorial. The mundane explanation posits that image releases are subject to standard calibration and review protocols. Raw data originating from spacecraft instruments is not disseminated immediately. It undergoes processing, error checking, calibration against established standards, and review by scientific teams before its eventual release. This procedure can extend over several weeks or months and does not inherently signify a cover-up. It is standard operational practice. A less mundane explanation suggests that the image contains information that is controversial, something that necessitates careful interpretation prior to public dissemination. If the image reveals anomalies, features inconsistent with the expected profile of a comet, NASA might delay its release until these anomalies are understood, thereby preventing the fueling of speculation or misinterpretation. This is not necessarily malicious. Space agencies have, in the past, faced difficulties when releasing data that was subsequently misinterpreted by the public or media, leading to the propagation of inaccurate narratives that are challenging to correct once they have gained traction. The conspiratorial explanation posits that NASA is aware of 3IATLAS's artificial nature and is managing the information flow to avert widespread panic or societal disruption. This explanation finds favor in certain online communities, but is also the least probable. Space agencies are not monolithic entities. They comprise thousands of scientists, engineers, and administrators, many of whom would likely not consent to the suppression of evidence indicating extraterrestrial technology. Leaks would be almost unavoidable. Furthermore, the scientific community operates under principles of transparency and peer review. Withholding data fundamentally undermines these principles and jeopardizes careers. It is difficult to envision a scenario where such a conspiracy could be successfully maintained. Nevertheless, the perception of data suppression can be nearly as damaging as the act itself. When prominent scientists like Loeb publicly advocate for transparency and receive no clear responses, it fosters distrust. Individuals begin to question, what are they concealing? Why are they not sharing all the information? Once these questions take root, they become exceedingly difficult to eradicate. The network announced a Comet campaign scheduled to run from November 2025 through January 2026. ION, the Interstellar Object Network, is a coalition of space agencies and observatories established to coordinate responses to potentially hazardous asteroids and comets. Initiating a campaign for 3IATLAS is logical if the object is sufficiently unusual to warrant coordinated observation. However, it also raises concerns. Is this merely standard procedure for an anomalous interstellar object, or does it indicate that agencies are more apprehensive than they outwardly express? Institutional incentives play a crucial role in this dynamic. Space agencies rely on public confidence and government funding for their operations. Prematurely speculating about extraterrestrial technology and subsequently proving incorrect could jeopardize their credibility. Politicians might question the allocation of funds. The media could portray them as reckless. Conversely, if they adopt an overly conservative stance, too cautious in acknowledging anomalies, they risk being accused of withholding information or neglecting significant questions. It is a precarious balancing act, and 3IATLAS is testing their equilibrium. Peer review and scientific caution are indispensable, yet they can also function as barriers to entry. When a novel idea challenges established thinking, it undergoes heightened scrutiny, which is appropriate. Extraordinary claims necessitate extraordinary evidence. However, there exists a risk that conservatism morphs into a reflexive response, where anomalies are dismissed not because the explanations are robust, but because the alternatives are unsettling. Confirmation bias can operate in both directions. One can be predisposed to perceiving aliens everywhere, or conversely predisposed to never seeing them, even when they are plainly apparent. Some mainstream experts in cometary and orbital dynamics have voiced criticism of Loeb's approach. They contend that he is selectively highlighting anomalies, focusing on data points that support his hypothesis while disregarding others that do not. They emphasize the inherent complexity of cometary activity, the uncertainties present in existing models, and assert that prematurely invoking artificial explanations before thoroughly exhausting natural ones is unwarranted. These are valid critiques. Scientific advancement is achieved through rigorous hypothesis testing, not by leaping to unsubstantiated conclusions. However, the question of what constitutes exhausting natural explanations also arises. How many models should be explored before considering alternative hypotheses? How weak must natural explanations become before speculation is deemed justified? There is no definitive answer, and this ambiguity is the locus of the controversy. Speculation regarding internal communications and unpublished data is unavoidable. It is possible that higher-resolution images exist but have not been released. Perhaps spectroscopic observations revealing unexpected features are also being withheld. There might be internal discussions among scientists weighing how to present findings without inadvertently causing misinterpretation. Alternatively, it is possible that none of this is true. No conspiracy, no hidden data, only the deliberate pace of the scientific process and the inherent delays associated with bureaucracy and peer review. The somewhat grainy quality of the released images from the Parker Solar Probe has also been questioned. Are these images indistinct due to the instrument's limited resolution, or is it a deliberate choice to release lower quality versions? The former scenario is more probable. The Parker Solar Probe's wide-field imager was primarily designed to study the Sun's corona, not faint interstellar objects. Imaging 3IATLAS pushed the instrument to its operational limits. The graininess is likely a reflection of these limitations rather than intentional obfuscation. Transparency in scientific endeavors is paramount, but it is also inherently complex. Scientists operate with incomplete data, uncertain models, and face pressure to be both meticulous and timely. When anomalies emerge, the temptation to speculate is strong, but so is the risk of error. Institutions strive to balance these competing pressures, but achieving equilibrium is challenging. In the current era of social media, every decision is subjected to intense scrutiny. Every delay is questioned, and every statement is analyzed for hidden meanings. If bias or delay is indeed present, what might it be concealing? And what would the physics of the situation look like if we allowed our imaginations to roam freely, unburdened by conservatism or excessive caution? Part 9 explores hypotheses rooted in physics and engineering. Let us assume, for the sake of argument, that 3IATLAS is artificial. Setting aside skepticism and conservatism, we must ask, what could it physically be? What engineering principles might explain its acceleration, its brightness, its color, and its trajectory? This inquiry, while speculative, is informed by physics and constrained by the available data. Let us begin with the concept of a light sail. Light sails are not merely the stuff of science fiction. They represent a tangible concept proposed by scientists and engineers as a viable method for interstellar travel. The underlying principle is straightforward. Photons carry momentum. When light strikes a reflective surface, it imparts momentum, generating a minute but measurable force. A sail characterized by a large surface area and minimal mass can, over time, be propelled by starlight, eventually achieving speeds that would necessitate enormous quantities of fuel for conventional rockets. For a light sail to generate the observed acceleration of 3IATLAS, a specific ratio of surface area to mass is required. The object would need to be extremely thin, perhaps only micrometers in thickness, and highly reflective, with an albedo approaching unity. Materials such as aluminized mylar or carbon fiber composites could potentially achieve these properties. At a distance of 1.36 astronomical units, the intensity of sunlight is less than at Earth's orbit, but it remains sufficiently strong to exert a force on a sufficiently large and lightweight sail. Performing the calculations, the radiation pressure at 1.36 astronomical units for a perfectly reflective surface is approximately 4.5 micronewtons per square meter. To achieve an acceleration of 135 kilometers per day squared, which translates to roughly 1.56 times 10 to the negative fourth meters per second squared, a specific area-to-mass ratio is necessary. If, for instance, the sail possesses an area of 1 square kilometer and a mass of a few hundred kilograms, the figures begin to align. While this represents a thin sail, it is not impossibly so. The challenge lies in the requirement that such a sail must withstand the rigors of interstellar space for potentially millions or billions of years. Cosmic rays, micrometeoroids, and interstellar dust would inevitably degrade its surface. The sail might be tattered, torn, or partially eroded by the time it reaches our solar system. Such degradation could account for the object's behavior deviating from that of a pristine sail. It might be tumbling, reflecting light asymmetrically, resulting in acceleration vectors that are contingent upon its orientation relative to the sun. Another plausible explanation involves an internal propulsion system. Spacecraft executing gravity-assist maneuvers frequently engage their engines at perihelion, the point of closest approach to a star or planet utilized for the assist. Firing engines at perihelion maximizes the efficiency of the burn because the spacecraft is moving at its highest velocity at that juncture, and the Oberth effect magnifies the change in velocity. If 3IATLAS were a spacecraft performing a powered gravity assist, it might have activated an engine near perihelion to modify its trajectory. What kind of engine could this be? Chemical rockets are improbable. They require fuel, and carrying sufficient fuel for a burn lasting days or weeks would necessitate a considerable mass, inconsistent with the observed acceleration. Electric propulsion systems, such as ion drives, could be a viable option. Ion drives generate low thrust over extended periods, achieving acceleration gradually but efficiently. However, ion drives require a power source, typically derived from solar panels or nuclear reactors. A spacecraft with a degraded power system might still possess the capability for low-thrust maneuvers. Alternatively, we might consider exotic propulsion methods. If the object originates from an advanced civilization, it could employ technologies beyond our current comprehension. It might manipulate electromagnetic fields or utilize some form of reactionless drive, although such drives would contravene the principle of conservation of momentum as currently understood. This line of speculation ventures into the realm of fantasy, but if we are entertaining the possibility of extraterrestrial technology, we cannot discount technologies that transcend our present understanding of physics. What about the materials themselves? If 3IATLAS is artificial, what is it composed of? Metals could explain its blue coloration and high reflectivity. Aluminum, titanium, or more specialized alloys might possess the requisite strength-to-mass ratios. Carbon composites present another possibility, being both lightweight and robust, capable of enduring harsh environments. Certain materials might exhibit unusual thermal properties, reflecting or emitting light in ways that do not conform to natural objects. Spectroscopic analysis could reveal material signatures. Metals possess characteristic absorption and emission lines. If 3IATLAS reflects sunlight with a spectrum exhibiting metallic absorption features, this would constitute definitive evidence. To date, published spectra have not indicated such features, but the resolution and signal-to-noise ratio of these spectra may be insufficient to detect subtle lines. Thermal infrared observations offer another avenue of investigation. If the object possesses an internal heat source, it would radiate more infrared energy than expected from a passive object heated solely by the sun. The James Webb Space Telescope, with its exceptional infrared sensitivity, could detect such excess emission. If observations conducted in December reveal thermal anomalies, this would strengthen the hypothesis of an artificial origin. Furthermore, there is the question of purpose. If 3IATLAS is artificial, what is its objective? Is it a probe dispatched to study our solar system? Is it derelict, a piece of ancient technology long since rendered inoperable? Could it be part of a larger network, a fleet of similar objects dispersed across the galaxy, tasked with monitoring or mapping stellar systems? Loeb employed the metaphor of a Trojan horse, suggesting an object that appears innocuous yet might harbor hidden payloads or functions. This metaphor is provocative, even unsettling, but it warrants consideration. Could the object be deploying smaller probes? Could it be shedding instruments as it traverses the solar system? While there's no concrete proof of this, a lack of evidence isn't proof of its absence. If such probes exist and are sufficiently small, current telescopes would struggle to detect them. Constructing a device engineered to endure billions of years in interstellar space presents a significant engineering hurdle. Exposure to radiation, repeated temperature fluctuations, and impacts from microscopic meteoroids would all contribute to material degradation over vast stretches of time. Any civilization possessing the capability to build such a sophisticated mechanism would need to anticipate and compensate for this degradation, perhaps through an overly robust design or the utilization of materials capable of self-repair. The continued operational status of 3IATLAS, if indeed it remains functional, implies either a very recent origin or an exceptionally resilient construction. This line of reasoning invariably steers us toward philosophical contemplation. If 3IATLAS is indeed an artificial construct and is still active, it suggests the existence of a civilization capable of interstellar travel, or at the very least, interstellar communication. It implies they have existed for a duration sufficient to dispatch such objects across the galaxy. It suggests we are not alone. Furthermore, it implies a deliberate interest, past or present, in celestial bodies such as our solar system. This very notion opens avenues of inquiry that extend far beyond mere orbital mechanics and the measurement of light intensity. Section 10. Implications for Scientific and Philosophical Culture. If 3IATLAS is artificial, what are the ramifications? Not solely for the field of astronomy, nor solely for our comprehension of comets and interstellar visitors, but for humanity's position within the cosmos, for our very sense of identity and our potential future trajectory. Let us begin with a statistical inquiry. The Milky Way galaxy harbors hundreds of billions of stars. A considerable number of these stars host planetary systems. Among these planets, some reside within habitable zones. A subset of these potentially habitable planets might foster the development of life. A fraction of those might evolve intelligent life. And a portion of these intelligent civilizations could potentially develop the technology necessary for interstellar communication. The Drake equation serves to formalize this progression of thought despite the inherent uncertainties surrounding the values of its variables. Nevertheless, even conservative estimations indicate the likely presence of numerous technological civilizations within our galaxy. So, where are they all? This is the essence of the Fermi paradox. If intelligent life is prevalent, why have we not encountered any evidence of it? Why have we not detected radio signals, monumental structures like Dyson spheres, or fleets of spacecraft? One possible explanation is that our search efforts have been insufficient, or perhaps misdirected. Another is that intelligent civilizations are exceedingly rare, short-lived, or prone to self-destruction, leaving us effectively alone, or nearly so, in this galaxy. A third possibility is that they, or their artifacts, are already present, and we have simply overlooked them due to an inability to recognize what to look for. 3IATLAS, if confirmed as artificial, would significantly shift the landscape of this debate. It would suggest that technological remnants are not as uncommon as we might have believed. It would imply that civilizations actively send objects into the galaxy, whether as exploratory probes, deliberate messages, or simply as byproducts of their activities. It would offer a resolution to the Fermi paradox, and that resolution would be, they are ubiquitous. We have simply been looking past them. The search for extraterrestrial intelligence, or SETI, has predominantly concentrated on radio and optical signals. Researchers have meticulously scanned the celestial sphere for narrow-band radio transmissions or laser pulses that might signify intentional communication. However, technological indicators can manifest in a multitude of forms. Gigantic constructions, such as Dyson spheres, would create discernible dips in starlight. Industrial pollution from advanced civilizations might be detectable in the spectral analysis of exoplanet atmospheres. Interstellar probes or remnants of their activities could traverse our solar system, exhibiting accelerations that cannot be solely attributed to gravitational forces. Avi Loeb has been a fervent proponent of broadening the scope of SETI to encompass the search for tangible artifacts. He has advocated for treating anomalous celestial objects with serious consideration, for investigating them with the same scientific rigor applied to radio SETI, and for asserting that dismissing them out of hand represents a deficiency in scientific imagination. His detractors contend that he is lowering the evidentiary threshold, willing to entertain extraordinary hypotheses without adequate substantiation. Both viewpoints possess merit. The inherent tension between them mirrors a broader discourse concerning how science ought to respond to unexplained phenomena. Scientific conservatism holds value. It serves to prevent erroneous conclusions. It ensures that assertions are rigorously vetted before widespread acceptance. However, this conservatism can also ossify into dogma, fostering an environment where certain inquiries are deemed off-limits and where researchers who dare to pose these questions face marginalization or ridicule. Loeb's readiness to push boundaries and to ask uncomfortable questions challenges this entrenched conservatism. Whether his assessment of 3IATLAS proves correct remains to be seen, but his methodological approach has already instigated a notable shift in the discourse. What would transpire if 3IATLAS were definitively confirmed as artificial? Policymakers would inevitably become involved. Governments would seek to ascertain, is it a potential threat? Is it still actively functioning? Can we establish communication with it? Can we retrieve it? National security agencies might express keen interest. The object could be classified, its data subjected to restrictions, or it might evolve into a focal point for international collaboration, a shared discovery transcending national boundaries. Funding for astronomical research and SETI initiatives would likely experience a substantial increase. If one interstellar artifact has been identified, it is plausible that others exist. Telescopes would be reallocated to systematically search for comparable objects. Proposals for missions involving interception or rendezvous would be formulated. The scientific community would coalesce in a manner not witnessed since the Apollo era. The cultural impact would be profound. Religious beliefs, philosophical frameworks, and prevailing worldviews would all undergo significant challenges. Certain religious traditions might readily embrace the discovery, interpreting it as confirmation of a universe teeming with divine creation. Others might grapple with the implications. Philosophers would engage in debates regarding humanity's significance in a cosmos where uniqueness is no longer assured. Researchers specializing in existential risks would pose the question, if civilizations dispatch probes, do they also deploy weapons? Is the galaxy a secure environment, or are we being naive by assuming benevolent intentions? Loeb has previously referenced the dark forest analogy, borrowed from the realm of science fiction. This concept posits that the galaxy might be a perilous expanse, where civilizations deliberately conceal themselves to evade detection by potentially hostile neighbors. If this premise holds true, then discovering evidence of other civilizations represents not merely a scientific milestone, but a potential existential threat. We might inadvertently be announcing our presence to entities that would prefer our continued silence. This is speculative, perhaps excessively pessimistic, yet it is a pertinent question that warrants consideration. Scenarios of contact range from benign to catastrophic. A defunct probe informs us that another intelligence exists, or once existed, without posing an immediate danger. An operational probe, however, raises inquiries about its purpose and intent. A hostile artifact represents a nightmarish prospect, though it is also the least probable given the immense distances and temporal scales involved. Public confidence in science and its institutions would be subjected to scrutiny. If the discovery is managed with transparency, if data is disseminated openly, and if the investigative process is both rigorous and inclusive, it could bolster public trust. Conversely, any perception of secrecy, any manipulation or spin applied to information could exacerbate cynicism and foster distrust. The manner in which we address 3IATLAS, irrespective of its ultimate nature, will establish precedents for how we handle future anomalies. Before fully venturing into the unknown, let us pause to consider other developments occurring at the forefront of scientific research and artificial intelligence. This is because 3IATLAS may represent merely the nascent stage of a new epoch, one where the distinctions between the natural and the artificial, between discovery and detection, and between our current knowledge and what we are about to learn are blurring at an unprecedented pace. Section 11. A recent cometary event. Comet C2022 R2 Swan. While 3IATLAS has garnered significant media attention, another celestial body made a close pass by the Sun in late October of the year 2025. Comet C2022 R2 Swan, initially detected by the SWAN instrument aboard the Solar and Heliospheric Observatory, provides a valuable point of comparison. To accurately assess the extent to which 3IATLAS deviates from the norm, a control subject is essential. A typical comet exhibiting predictable behavior, allowing for a quantifiable measurement of any differences. Comet Swan followed an orbital path that brought it within approximately 0.88 astronomical units of the Sun, a closer approach than 3IATLAS, yet still beyond Earth's orbit. As it approached its closest point to the Sun, perihelion, it increased in brightness, developed a visible coma and tail, and displayed all the characteristics astronomers anticipate from a sun-grazing comet. Photometric observations meticulously tracked its luminosity over time, and the resulting curve adhered to a more conventional power law with an exponent closely approximating -3. Well within the expected range of normal cometary activity. Spectroscopic analysis of SWAN revealed the presence of water vapor, carbon monoxide, and dust. The rates at which gases were being emitted were consistent with models predicting the behavior of a comet of its estimated size and composition. There were no unexpected findings. The object behaved precisely as cometary physics dictates. Ice sublimates under solar heat. Gas jets generate propulsion. Dust particles scatter sunlight, and the object's brightness escalates in direct proportion to the volume of material expelled. A comparison between SWAN and 3IATLAS vividly highlights their disparities. SWAN exhibited pronounced gas emissions, whereas 3IATLAS did not. SWAN's brightness progression followed established models, while 3IATLAS's curve was steeper. SWAN possessed a color typical of comets, whereas 3IATLAS appeared distinctly bluish. Each of these differences, when considered in isolation, might be attributable to variations in composition, structural integrity, or activity patterns. However, when viewed collectively, they paint a picture of two fundamentally dissimilar entities. One interpretation suggests that 3IATLAS is simply an extreme manifestation of natural phenomena, a comet possessing unusual characteristics that push the boundaries of what is conceivable within natural processes. Comets exhibit considerable diversity. They originate in varied regions of protoplanetary disks, accrete different materials, and undergo distinct thermal histories. Some are water-rich, while others are dominated by carbon dioxide. Some possess porous, loosely bound structures, while others are dense and compact. It is entirely plausible that 3I-ATLAS represents an outlier on this spectrum of diversity. Another interpretation posits that the distinctions between SWAN and 3I-ATLAS are not merely quantitative, but fundamentally qualitative. SWAN is a comet. 3I-ATLAS is something else entirely. The absence of significant gas emission despite notable acceleration, the unconventional brightness curve, and the unusual blue hue could all serve as indicators of a non-natural origin. This interpretation, while more speculative, remains consistent with the observed data. The insights gained from monitoring SWAN offer valuable guidance for our approach to investigating 3I-ATLAS. Ground-based observatories meticulously tracked SWAN using photometry and spectroscopy, constructing a detailed chronicle of its activity over several weeks. These identical techniques are being employed for 3I-ATLAS, albeit with the added complexities of its fainter magnitude, greater distance, and reduced activity. These factors render observations more challenging, the data more susceptible to noise, and the conclusions more tentative. If SWAN exhibits normal behavior and 3I-ATLAS behaves anomalously, this strengthens the argument for 3I-ATLAS being unusual. Conversely, if SWAN also displayed peculiar features, unexpected spikes in brightness, weak gas emissions, or unusual coloration, it would suggest that our current models require comprehensive revision. To date, SWAN appears typical, which, by contrast, renders 3I-ATLAS more suspicious. The morphology of the dust tail presents another avenue for comparison. SWAN's tail clearly depicted the classic sunward repulsion, bending away from the sun due to the pressure exerted by sunlight on dust particles. The shape and intensity of the tail aligned with models predicting the behavior of dust grains of varying sizes propelled by solar radiation. Should 3I-ATLAS develop a comparable tail, it would lend support to the hypothesis of a natural comet. If its tail, should one form, presents a different appearance, excessively straight, remarkably faint, or unusually reflective, this could serve as another clue pointing towards an anomaly. The patterns of cometary activity can vary dramatically. Some comets experience sudden outbursts, characterized by abrupt increases in brightness caused by the explosive release of subsurface volatile substances. Others exhibit a steady brightening. Some diminish rapidly after perihelion, while others maintain their activity for extended periods. Comprehending this inherent variability is paramount to accurately interpreting the behavior of 3I-ATLAS. Does its observed activity fall within the spectrum of natural variations, or does it lie outside these parameters in a manner that necessitates alternative explanations? Spacecraft observations of SWAN, if any were undertaken, could provide higher-resolution data than ground-based telescopes. Solar observatories such as SOHO or the Parker Solar Probe might have captured relevant images or spectral data. Such observations, if available and publicly disclosed, could refine our understanding of typical cometary behavior and establish a benchmark against which 3I-ATLAS can be evaluated. The fundamental conclusion is this: SWAN represents what we anticipate. It is the textbook example, a comet whose behavior aligns perfectly with the models we have meticulously developed over decades of observation and theoretical advancement. 3I-ATLAS, however, does not. It is the outlier, the anomaly, the data point that defies conventional explanation. And in the realm of science, outliers are either indicative of errors, mere statistical flukes, or the nascent seeds of entirely new understanding. Ascertaining which of these categories 3I-ATLAS belongs to is the crucial task that lies ahead. Section 12. A novel spectroscopic survey instrument, the first cosmic view from foremost. While individual celestial objects like 3IATLAS tend to capture public attention, the broader endeavor of mapping the galaxy is making significant progress through extensive large-scale surveys. One of the most recent additions to this initiative is the 4-meter multi-object spectroscopic telescope, or FORMOST, which has recently been deployed and is now yielding its initial scientific data. FORMOST is engineered to conduct wide-field spectroscopy, simultaneously capturing the spectral signatures of thousands of stars, galaxies, and other astronomical entities. Spectroscopy serves as the bedrock of contemporary astronomy. By dissecting light into its constituent wavelengths, astronomers can ascertain the chemical composition, temperature, density, and motion of distant objects. A single spectrum can reveal whether a star is metal-rich or metal-poor, whether a galaxy is actively forming stars or is quiescent, and whether an object is approaching or receding from us. When this capability is applied to thousands of targets concurrently, a comprehensive depiction of the galaxy's structure, historical evolution, and constituent elements begins to emerge. FORMOST's inaugural data release, sometimes referred to as the first cosmic view, encompasses spectra of stars residing within the Milky Way's disk and halo, galaxies at varying cosmological distances, redshifts, and other objects of notable interest. The sheer volume of data generated is astounding. Each night of observational activity yields spectra for thousands of targets. Over the course of months and years, the survey is projected to accumulate millions of spectra, thereby creating a valuable repository that astronomers will mine for decades to come. Why is this significant for interstellar objects such as 3IATLAS? Because large-scale surveys fundamentally enhance our capacity to detect anomalies. When examining a single object, it is inherently difficult to determine if it is unusual. There is no established baseline for comparison. However, when scrutinizing millions of objects, emergent patterns become apparent. This enables the identification of outliers, objects exhibiting unexpected chemical abundances, peculiar kinematic behaviors, or anomalous spectral features. These outliers are often the most captivating because they deviate from established models, compelling us to pose entirely new questions. Hypervelocity stars serve as a prime example. These are stars moving at such extreme speeds that they are escaping the galaxy's gravitational embrace. Their discovery was facilitated by comprehensive large-scale surveys that measured the velocities of a multitude of stars, flagging those moving at exceptionally high speeds. Once identified, hypervelocity stars became subjects of intensive investigation. What are their origins? How did they acquire such immense velocity? The prevailing hypothesis suggests they were ejected from the galactic center due to interactions with the supermassive black hole. However, alternative mechanisms are also conceivable. Chemically unusual stars represent another category. The majority of stars possess compositions akin to our Sun, with variations contingent upon their formation location and epoch. Nevertheless, surveys occasionally uncover stars with elemental abundances that do not align with any known stellar population. These stars might represent survivals from the galaxy's primordial past, or they could have formed in exceptionally unique environments. In either scenario, they offer clues to processes that we do not yet fully comprehend. Interstellar objects could be similarly identified by surveys like FORMOST. If an object's spectrum fails to match any catalogued comet, asteroid, or stellar classification, it is flagged for further examination. Similarly, if an object exhibits unusual motion, moving too rapidly or in an unexpected trajectory, it is designated for follow-up study. The more objects subjected to survey, the greater the probability of discovering the rare, the peculiar, the anomalous. Foremost also contributes to the intricate task of mapping the structure of the Milky Way. By precisely measuring the chemical abundances and velocities of stars, astronomers can reconstruct the galaxy's historical trajectory, identifying past merger events, stellar migration patterns, and the distribution of various stellar populations. This foundational work is indispensable for comprehending the origins of interstellar objects like 3I-ATLAS. If we possess a clear understanding of the kinematics associated with different stellar populations, we can effectively trace backward, estimating which stellar groups or regions an interstellar object might have originated from. There exists a thematic resonance here. Just as 3I-ATLAS challenges our understanding of individual celestial bodies, large-scale surveys confront our comprehension of populations and distributions. Both approaches, the meticulous examination of individual anomalies and the statistical analysis of extensive datasets, are critically important. We require the surveys to locate these anomalies, and we need detailed follow-up investigations to elucidate the factors that render them anomalous. The future of anomaly detection may well involve the integration of artificial intelligence. Machine learning algorithms are exceptionally adept at pattern recognition and the identification of outliers. By training an algorithm on millions of standard spectral profiles, it can effectively flag those that deviate from the norm. Applying such an algorithm to survey data from foremost or analogous instruments transforms it into a tireless seeker of the unusual, the unexpected, and the potentially revolutionary. Envision an artificial intelligence system meticulously trained on every recorded spectrum of every comet ever observed. If fed the spectrum of 3I-ATLAS, it could calculate the probability of this object being a natural comet. If this probability registers as low, the system would flag it for human review. Scaling this process across the entirety of the sky, encompassing all wavelengths and all observational modalities, would result in the creation of a detection network sensitive to anomalies that might otherwise elude our notice. This paradigm is already being implemented in other areas of astronomical research. AI algorithms have been instrumental in the discovery of novel types of gravitational lenses, the identification of unusual variable stars, and the classification of millions of galaxies. Applying these same techniques to the search for interstellar objects or technosignatures represents a logical progression. The primary challenge lies in precisely defining the parameters of what we are seeking. AI can discern patterns, but it is ultimately humans who must determine the significance of those patterns. The connection between Foremost and 3I-ATLAS is more than merely metaphorical. If interstellar objects are indeed common, as population models suggest, then wide-area surveys are poised to discover more of them. Each such discovery will contribute to our growing body of knowledge. Each anomaly will refine our existing models, and eventually we will amass sufficient data to definitively ascertain whether objects like 3I-ATLAS represent extreme natural occurrences or something entirely different. Foremost exemplifies a broader trend unfolding within astronomy, the transition from targeted observations to comprehensive surveys. Rather than directing telescopes toward specific celestial bodies selected for particular reasons, we are now engaged in mapping and cataloging everything, allowing the data itself to reveal patterns we had not previously anticipated. This represents a democratization of discovery where unexpected findings can emerge from any quadrant of the sky. And this brings us to the compelling possibility that 3I-ATLAS is not a solitary instance. Perhaps it is merely the vanguard of many. It is conceivable that the next generation of surveys will uncover dozens or even hundreds of comparable objects, each possessing its own unique anomalies and posing the same profound, perhaps unsettling, questions. If such a scenario unfolds, the ensuing debate will shift from the question of whether any individual object is artificial to what the statistical distribution of such findings reveals about the prevalence of technological artifacts within our galaxy. This is a future worthy of deep reflection, yet it is also a future contingent upon the very instruments we are presently developing. Instruments such as those provided by Foremost, which augment our capacity to observe, quantify, and comprehend the universe in all its intricate detail. Part 13. A predictive model for meteor shower activity in 2025. The Drainid outburst prediction for October of 2025. In October of 2025, Earth navigated through the particulate trail shed by Comet 201P Giacobini-Zinner, resulting in the annual Draconid meteor shower. This year's celestial display was anticipated to be more vigorous than usual, potentially reaching outburst levels, a projection derived from meticulous simulations of the comet's debris path. These forecasts originated from investigators like Jeremy Vaubalon and Peter Jenniskens, who have dedicated years to refining computational models that describe the evolution and dispersion of cometary dust along orbital trajectories. Meteor showers are events that can be reliably predicted. When a comet approaches the Sun, it liberates dust and fragmented material. This detritus subsequently disperses along the comet's orbital path, forming a stream. When Earth's trajectory intersects this stream, the dust particles enter our atmosphere at extreme velocities, generating intense heat and producing the luminous streaks we perceive as meteors. The shower's intensity is dictated by the quantity of dust expelled by the comet, the density of the resulting stream, and the precise geometry of Earth's passage through it. Modeling meteor showers necessitates an understanding of dust dynamics. Particles of varying dimensions are subject to differential influences from solar radiation pressure and gravitational disturbances. Minute particles are propelled outward by the sun's rays, spreading at a more accelerated rate than their larger counterparts. Over extended periods, the stream gradually dissipates, becoming more diffuse yet simultaneously more elongated. By simulating these phenomena, researchers can forecast the timing and location of meteor showers, sometimes with predictions extending years or even decades into the future. The parallels to cometary outgassing and the formation of dust tails are strikingly evident. When one models a meteor shower, the fundamental process being simulated is the movement of particulate matter influenced by solar radiation, planetary gravitational forces, and the initial momentum imparted by the comet's outgassing. The identical physical principles govern celestial bodies, such as 3IATLAS. If 3IATLAS is indeed a comet that generates dust, then that dust ought to form a tail, reflect solar illumination, and evolve in predictable ways contingent upon particle size and chemical composition. The remarkable accuracy of meteor shower models, where predictions align with observational data with high fidelity, serves as a testament to our profound understanding of dust dynamics, at least concerning typical cometary material. Consequently, when an object like 3IATLAS deviates from these established models, it warrants thorough investigation. Could its composition be atypical? Is its dust production episodic? Are there other underlying factors at play? The predictions for the 2025 Draconid outburst were predicated on particles ejected by Comet Giacobini-Zinner during specific past passages near the Sun. By tracing the predicted trajectory of these particles forward in time, factoring in gravitational perturbations from planets and solar radiation pressure, researchers calculated that Earth would traverse a particularly concentrated filament of this debris stream. The predicted window for this event was exceedingly narrow, possibly spanning only a few hours, presenting a significant observational challenge, yet a notable validation for the predictive models. If the forecasts proved accurate and initial reports suggested they were indeed precise, this would affirm the fundamental physics underpinning them. It would demonstrate that when all forces acting upon dust particles are adequately accounted for, the resulting predictions accurately mirror reality. Such validation is crucial as it instills confidence in applying the same modeling techniques to other celestial objects. However, there's a crucial caveat. Meteor shower models function effectively because the parent comet's characteristics are generally known: its orbit, its activity history, and its composition. These models can be calibrated against observations from multiple appearances of the comet. In the case of an interstellar object like 3IATLAS, this historical data is absent. We observe it during a single transit through our solar system, necessitating the inference of all properties from this isolated snapshot. This significantly complicates the modeling process and amplifies the inherent uncertainties. Furthermore, questions arise regarding the completeness of our current models. Are there dust dynamics processes that remain poorly understood? Could there be irregularities in dust generation or ejection that our models fail to capture? The modeling for the Draconid outburst, while sophisticated, still rests on assumptions regarding particle size distributions, ejection velocities, and surface properties. Any inaccuracies in these assumptions can lead to erroneous predictions. Some researchers have posited that observed anomalies in meteor shower activity, such as unexpected peaks or temporal gaps, might signify previously undiscovered processes. It's conceivable that comets may, on occasion, produce bursts of exceedingly fine dust that disperses far more rapidly than current models anticipate. Alternatively, surface modifications could alter ejection velocities in ways we have not yet accounted for. These represent active avenues of scientific inquiry and hold relevance for understanding objects such as 3IATLAS. The connection here is methodological. Both the forecasting of meteor showers and the modeling of cometary activity depend on comprehending the motion of minuscule particles under the influence of intricate forces. Both necessitate detailed computational simulations and are rigorously tested against observational data. When these models perform as expected, they bolster our confidence. When they falter, they highlight gaps in our comprehension. 3IATLAS might be illuminating such a deficiency, a point where our models of cometary behavior break down or require refinement, or it could signify something entirely different. If the object is artificial in origin, then dust dynamics models may be inapplicable or only partially relevant. A rotating solar sail or a disintegrating spacecraft could generate luminosity fluctuations that superficially resemble dust tails, but without adhering to the same physical principles. Differentiating between these possibilities demands observations of sufficient resolution to discern fine details, which is precisely the objective of the forthcoming observational campaigns. The Draconid shower also serves as a salient reminder that the solar system is not a void. It is replete with debris, dust, and particles shed by comets and asteroids over eons. The vast majority of this material is naturally occurring, a residual byproduct of solar system formation and evolution. However, from a statistical standpoint, if interstellar objects periodically traverse our celestial neighborhood, it is plausible that some might also contribute debris. Could fragments of 3IATLAS, if it is artificial and undergoing degradation, become integrated into the interplanetary dust environment? Might future meteor showers possess an interstellar component? These are indeed speculative queries, but they are not entirely without merit. If technologically advanced civilizations are prevalent throughout the galaxy and dispatch probes or artifacts, then a fraction of the interplanetary dust could potentially be of artificial provenance. Detecting such material would necessitate novel observational techniques, the deployment of new instruments, and a willingness to search for signatures previously unimagined. Part 14, an artificial intelligence technology story, OpenAI and AMD hardware partnership. In late October of 2025, OpenAI unveiled a significant collaboration with AMD, securing access to cutting-edge graphics processing unit (GPU) infrastructure essential for the training and deployment of extensive artificial intelligence models. This agreement represents an investment in the billions of dollars worth of computational power and underscores the escalating competition in AI development, where access to robust hardware is as crucial as breakthroughs in algorithmic design. Why is this development pertinent to astronomy? Specifically, to the endeavor of searching for interstellar objects and to the fundamental question of whether 3IATLAS is a natural or artificial phenomenon? Because computational power has emerged as the new paradigm for astronomical observation. Increased computational capacity allows for the processing of greater volumes of data, the execution of more complex simulations, and the detection of a wider array of patterns. Artificial intelligence is fundamentally reshaping scientific methodologies, with astronomy standing at the vanguard of this transformation. Consider the sheer magnitude of contemporary astronomical surveys. Observatories like the Vera C. Rubin Observatory, once operational, are projected to generate terabytes of data nightly, capturing images of billions of stars, galaxies, transient celestial events, and moving objects. No single human, or even a team of humans, could possibly analyze such an overwhelming volume of information. However, AI possesses this capability. Machine learning algorithms are adept at scanning imagery, identifying and classifying objects, flagging anomalies, and prioritizing targets for subsequent investigation, all in real time. This functionality is already being actively utilized. The Zwicky Transient Facility employs AI to identify supernovae, variable stars, and other transient phenomena from its nightly observational data. Its algorithms process images, subtract background stellar noise, and highlight changes. While human astronomers review the flagged events, the AI performs the initial data filtering, thereby enabling the management of the immense data stream. Now, apply this principle to the realm of interstellar objects. Envision an AI system trained on the imagery and spectral data of every comet, asteroid, and meteor ever recorded. This algorithm would learn to recognize typical characteristics, understand how comets brighten, how they move, and the composition of their spectral signatures. Upon the detection of a novel object, the AI would analyze it and compute a normalcy score. A high score would indicate a probable natural origin, while a low score would trigger a flag for more detailed follow-up. Such a system could have potentially identified 3IATLAS as anomalous at an earlier stage, perhaps noting its unusual brightness progression, faint gaseous emissions, or peculiar coloration, and issuing an alert before the object reached its closest approach to the Sun. This would have afforded astronomers more time to plan observations, increased opportunities for data acquisition, and a greater likelihood of resolving the enigmas surrounding the object. The strategic alliance between OpenAI and AMD is emblematic of a broader industry trend. The industrialization of AI, particularly the training of large-scale models, necessitates substantial computational resources, and corporations are actively vying to secure these capabilities. However, the advantages extend beyond commercial applications. Scientific research is increasingly reliant on the same technological approaches and infrastructure. Collaborations between technology firms and academic institutions are becoming commonplace and are significantly accelerating the pace of discovery. Furthermore, there is the critical aspect of AI-driven simulation, encompassing the modeling of cometary behavior, orbital dynamics, and dust evolution. All these areas involve complex physics that are computationally intensive. AI can expedite these simulations either by learning simplified models that execute more rapidly or by optimizing the numerical methodologies employed in traditional simulations. Faster simulations translate to the ability to test a greater number of scenarios, explore broader parameter spaces, and evaluate a larger number of hypotheses. Imagine conducting 1,000,000 simulations of cometary outgassing, varying parameters such as composition, structure, rotation rate, and surface properties to ascertain which combinations yield brightness curves analogous to that of 3IATLAS. Traditional methods could require months to achieve this, whereas AI-accelerated simulation might accomplish it in mere days or hours. This acceleration is paramount when attempting to interpret data from an object that is receding from the sun, fading from view, and presenting a limited observational window. AI could also contribute to the strategic planning of observational campaigns. Given constraints related to telescope availability, object visibility, and specific scientific objectives, an AI could optimize the scheduling, prioritizing observations that maximize the informational yield. This type of scheduling problem is inherently complex, involving numerous variables and trade-offs, but it represents precisely the kind of challenge at which AI excels. A more cautionary aspect also warrants consideration. As AI capabilities advance, their internal workings can become increasingly opaque. Neural networks trained on extensive data sets can generate remarkably accurate predictions, but deciphering the rationale behind those predictions often proves difficult. If an AI flags 3IATLAS as anomalous, can we confidently accept that assessment? What if the algorithm is inadvertently identifying artifacts within the data, biases present in the training dataset, or patterns that lack genuine physical significance? This presents the challenge of interpretability. Scientific inquiry demands comprehension, not merely prediction. If an AI indicates that an object is unusual, scientists need to understand the specific features that triggered the alert and ascertain whether those features are real or illusory. The development of interpretable AI systems is an active area of research and is indispensable for scientific applications. The synergy between AI development and scientific discovery is mutually beneficial. AI requires data for training, and science generates vast quantities of it. Science necessitates sophisticated computational tools to process this data, and AI provides them. As both fields progress, their interdependence will deepen, and groundbreaking discoveries like that of 3IATLAS will undoubtedly benefit from this amplified synergy. The future may well witness the advent of AI telescopes, integrated systems capable of performing observation, analysis, and decision-making in real time. An anomaly is detected by a telescope. An AI analyzes its characteristics, flags it as potentially artificial, and autonomously schedules follow-up observations with other instruments. Human oversight remains integral for final determinations and interpretation of results, but the AI assumes the burden of intensive data processing and pattern recognition. This future is perhaps closer than we might imagine, and it compels us to consider what we might uncover when we begin to observe not solely with our biological senses, but with artificial minds. Silicon intelligences capable of discerning patterns that have eluded us. Part 15. An Artificial Intelligence Policy Story, California's New AI Transparency Law. In September of 2025, the state of California enacted landmark legislation that holds the potential to significantly influence the future of human-machine interaction. Informally known as the AI Transparency Act, this new statute mandates that all artificial intelligence systems engaging with the public, including chatbots, virtual assistants, voice interfaces, and media generated by AI, must clearly identify themselves as non-human. The objective is both straightforward and profoundly significant. No AI should possess the ability to impersonate a human being. Whether interacting with a customer service bot, perusing an AI-authored article, or listening to a synthesized voice, individuals are entitled to know that they are engaging with artificial intelligence. Companies that fail to comply with this disclosure requirement face substantial fines, penalties, and considerable reputational damage. This legislation represents a legal acknowledgement that in an era saturated with synthetic content, the very concept of authenticity has become increasingly precarious. This law emerged from a growing sense of apprehension. The proliferation of deepfakes, AI-driven disinformation campaigns, and increasingly human-like digital personas has increasingly blurred the lines between the real and the artificial. As individuals find it progressively challenging to discern the difference, a dangerous erosion of trust can ensue. When the veracity of what one sees or hears becomes questionable, the very foundation of a shared reality begins to disintegrate. However, the implications of California's AI legislation extend far beyond the realms of social media or political discourse. They touch upon something more fundamental, something integral to the mechanisms by which society establishes trust, not only in technology but in science itself. The parallels are strikingly evident. Just as we demand transparency from AI systems regarding their nature, we also expect scientific institutions to be forthcoming about their knowledge and its limitations, particularly when the subject matter has cosmic implications. This brings us back to 3IATLAS. If this interstellar object proves to be artificial, or if even a shred of credible evidence suggests such a conclusion, it will undoubtedly ignite one of the most profound debates in human history. In such a scenario, transparency will transcend mere virtue, becoming an absolute necessity. Every decision made by NASA, every dataset released or withheld, every interpretation put forth will be subjected to exhaustive scrutiny. The public will demand complete access to information, as trust serves as the fundamental currency in both the technological and scientific domains. When engaging with an AI, we desire assurance of human oversight. When encountering a scientific claim, we seek confirmation that it is firmly rooted in empirical data rather than mere conjecture. Transparency cultivates this trust. Opacity erodes it. In an epoch where information traverses the globe instantaneously and where experts and influencers share the same digital stage, the demand for transparency has never been greater, nor its fulfillment more challenging. The California law reflects a pervasive societal anxiety, a fear that the very nature of reality is becoming increasingly indistinct. Deepfake videos can convincingly mimic world leaders, fabricate news events, or resurrect the voices of deceased individuals. AI-generated text can be indistinguishable from human writing, and synthetic voices can impersonate anyone with chilling accuracy. As the distinctions between truth and fabrication erode, societies risk losing their collective grasp on what constitutes reality. This is why labeling AI-generated content is not solely an ethical consideration. It is essential for preserving epistemic stability, the shared conviction that factual information remains verifiable. Science, too, is experiencing this seismic shift. When data points diverge from established theories, or when an object like 3IATLAS exhibits acceleration that cannot be explained by gravitational forces alone, similar questions of authenticity arise. Are we observing a genuine phenomenon, or is it an error, a misinterpretation? Scientific institutions, much like AI companies, face a delicate balancing act. Releasing unverified data prematurely can precipitate chaos, while undue delay can allow rumors to fill the void. We have witnessed this dynamic repeatedly, from initial reports of gravitational waves to pandemic data releases and controversial UFO disclosures. Transparency is no longer a controlled dissemination. It has become a battleground, and 3IATLAS occupies a pivotal position on this front line. If its anomalous acceleration is substantiated and definitively cannot be attributed to outgassing or dust physics, the public will demand access to the raw data, the astrometric measurements, the photometric calibrations, the simulation models, and the residual calculations. They will need to know who conducted the analysis, how potential biases were mitigated, and whether independent verification is currently underway. In such a circumstance, scientific confidentiality would become untenable, and the imperative for complete transparency would rival anything witnessed in modern scientific history. The AI Transparency Act not only enforces disclosure, but also mandates accountability. If an AI system deceives a user, legal recourse is available. If a company leverages AI to mislead the public, there will be consequences. This legislation establishes a chain of responsibility in a domain that was previously characterized by ambiguity. Could science ever operate under a comparable framework? Might there be mechanisms for holding institutions accountable for withholding critical data or misrepresenting their findings? This is a complex question. Science is not equivalent to commerce, and the pursuit of discovery is not regulated in the same manner as consumer protection. The established checks and balances within research, peer review, replication, open discourse, require time. They are designed to ensure rigor, not speed. However, when an anomaly such as 3IATLAS captures global attention, time becomes an exceedingly scarce commodity. Information disseminates instantaneously, and misinterpretations spread even more rapidly. In such an environment, scientific accountability may require significant evolution. Some experts have proposed the establishment of independent oversight bodies for extraordinary claims, committees tasked with rapidly evaluating evidence pertaining to technosignatures, unidentified aerial phenomena, UAP, or interstellar anomalies before they enter the public domain. Analogous to the Intergovernmental Panel on Climate Change, IPCC, such a panel could provide standardized frameworks for evidence evaluation, thereby assisting in distinguishing credible anomalies from sensational claims. However, this approach also carries inherent risks. Oversight can readily devolve into gatekeeping. If every unconventional finding necessitates bureaucratic approval before public discussion, open exploration could be stifled. Scientists might hesitate to share preliminary results for fear of negative repercussions, potentially delaying or obscuring genuine discoveries. Once again, the perpetual tension between openness and responsibility emerges as the defining characteristic of this era. The California law does more than simply alter behavior. It reshapes societal norms. It communicates that we expect honesty from our machines, a cultural shift as significant as any legal one. Science, too, is defined by its norms: peer review, reproducibility, skepticism. However, these norms were forged in a slower, quieter era, an age when discoveries took months to publish and public reactions unfolded in newspapers, not viral social media posts. Now, a single dataset or an ambiguous graph can electrify social media within minutes, with the world forming an opinion before peer reviewers have even opened their emails. Perhaps it is time for a new norm in scientific transparency, one that effectively bridges expert communication and public comprehension. This involves not indiscriminate data dumps, but curated transparency, clear explanations, real-time updates, and an open acknowledgement of uncertainty. Transparency does not equate to oversharing. It signifies forthrightness regarding what is known, what remains unknown, and the ongoing efforts to acquire further knowledge. When NASA or ESA releases preliminary data concerning 3IATLAS, they confront a triple challenge: communicating clearly to the public, fostering trust, and maintaining an unimpeachable reputation are paramount. Overly technical language alienates the general population, while excessive vagueness creates fertile ground for speculative theories. The delicate equilibrium between lucidity and circumspection is precisely the most challenging aspect to uphold. This is precisely why the discourse surrounding AI accountability bears such a striking resemblance to the ongoing challenges in scientific communication. Both rely on openness to cultivate confidence, and both face collapse if that trust is eroded. The recently enacted legislation governing artificial intelligence grants regulatory bodies the authority to mandate transparency. These authorities possess the capacity to scrutinize computational processes, require detailed disclosures, and impose penalties. While a comparable level of oversight is not yet established for scientific peculiarities, discussions regarding such protocols are now commencing. Within the scientific community dedicated to the search for extraterrestrial intelligence, there have been private deliberations concerning the necessity of developing protocols for handling anomalies. Predetermined courses of action should something truly inexplicable be discovered. Who would be authorized to provide confirmation? Who would be the initial spokesperson? How would the gathered information be validated and disseminated? These are questions we have never been compelled to address with such gravity until this juncture. The object designated Oumuamua might well represent the inaugural genuine test case. Should the subsequent phase of observations reveal sustained acceleration independent of gravitational influence, unaccompanied by any discernible gaseous emissions, the scientific establishment will be subjected to unprecedented public scrutiny. Every moment of hesitation, every delay in disclosure will be construed as an attempt to suppress information. Each official pronouncement will be meticulously analyzed for hidden meanings. The crucial lesson derived from California's legislative precedent is unequivocal. Transparency must be a proactive endeavor, not a retrospective reaction. Once public confidence erodes, its restoration becomes an exceedingly formidable, if not impossible, undertaking. There exists an additional layer to this situation, a deeply ingrained human emotional response. Regulations mandating AI transparency are a consequence of people's discomfort with being misled, even if the deception is unintentional. They desire to know when they are interacting with an entity that is not human. This fundamental emotional need for candor extends equally to how individuals perceive and react to scientific organizations. Should NASA, or any similar institution, ever present evidence suggesting alien technology, even preliminary indications, the resulting emotional upheaval would be profound. Individuals would crave reassurance that the evidence is authentic, that it has undergone rigorous verification, and that it is not being manipulated or deliberately withheld. While science fiction has prepared humanity for the prospect of contact, it has not adequately prepared us for ambiguity. What if humanity's first encounter with extraterrestrial intelligence is not a distinct signal emanating from the cosmos, but rather a subtle anomaly, a glint of manufactured material in a place it should not be, a faint trajectory that defies known physical laws? What if it resembles Oumuamua, existing in a state of uncertainty, neither definitively identified nor conclusively disproven? The true challenge will transcend mere data interpretation. It will involve managing collective public perception during a moment of profound intellectual disruption. It is perhaps no mere coincidence that both the field of artificial intelligence and the discipline of astronomy are grappling with the identical fundamental question: how to achieve transparency regarding the unknown. Artificial intelligence probes: how do we ensure individuals are aware when they are engaging with an intelligence that is not human? Astronomy, on the other hand, queries: how do we effectively communicate when we may have discovered an intelligence that is not human? Both questions converge on the same uncharted territory: the dissolution of clear demarcations between the known and the unknowable. Oumuamua, irrespective of whether its origin is cometary or artificial, currently occupies this very boundary. The manner in which we address this phenomenon, how we analyze, communicate, and disclose our findings, will profoundly influence humanity's preparedness for whatever future discoveries may arise. At present, Oumuamua is diminishing. It is receding from the sun, its luminescence fading as it retreats back into the vast darkness of interstellar space. However, the narrative is far from concluded. Upcoming observations from missions like JUICE and the James Webb Space Telescope, alongside data from terrestrial observatories, may yet provide definitive answers or further deepen the enigma. As these results become available, the public will not merely observe the scientific data, they will scrutinize the process itself: how it is shared, who is interpreting it, and whether the involved institutions genuinely embody the principles of transparency they profess. Because, ultimately, the way we navigate this critical juncture will have repercussions extending far beyond the realm of astronomy. It will establish a precedent for how humanity confronts all future anomalies and all future instances of cosmic uncertainty. Should Oumuamua ultimately prove to be a comet exhibiting unusual characteristics, the immediate story may fade, but the enduring lessons concerning trust and transparency will persist. If, however, it is determined to be something else entirely, then all aspects of our understanding will transform, not just our scientific paradigms and our comprehension of the universe, but our very perception of ourselves. For if Oumuamua is indeed of artificial origin, then humanity's first encounter with extraterrestrial intelligence did not manifest as a radio signal, a broadcast, or a deliberate message. Instead, it arrived as a profound test of our collective integrity, an examination of our capacity to confront the unknown with honesty, openness, and an absence of distortion. Perhaps the first piece of alien technology that humanity ever identifies will not solely reveal the existence of extraterrestrials. It may, in fact, reveal us, our deepest fears, our inherent limitations, and our readiness to embrace truth, even when that truth feels overwhelmingly immense.